Download this code from codegive.com, link in the description below. OK, let's dive into episode 6 of our Buffer Overflow 101 series, Finding Bad Characters. This is a crucial step in crafting reliable exploits because certain bytes can prematurely terminate your payload, rendering it useless. We'll cover the theory, the process, the code, and potential pitfalls. Episode 6, Hunting the Bad Guys, Identifying Bad Characters. 1. Why are bad characters important? Imagine you've carefully crafted a payload to overwrite the return address on the stack, redirecting execution to your shellcode. Everything looks perfect. You launch the exploit, and nothing happens. Or worse, the application crashes unexpectedly. What went wrong? The culprit might be bad characters. These are specific bytes that cause issues during the transfer or interpretation of your payload. Here's how they wreak havoc. String termination. Many C functions, like strcpy, strlen, and printf, rely on a null byte, \x00, to indicate the end of a string. If a null byte appears within your shellcode, the function will stop reading there, effectively truncating your payload. Function interpretation. Certain characters might be interpreted as control codes, escape sequences, or format specifiers by the application or the underlying libraries. For instance, *x0a, new line/line feed might be interpreted as the end of a line or trigger some input processing logic. *x0d, carriage return similar to new line. *x09, tab might be interpreted as a separator, causing the application to misparse your payload. Format specifiers like %s, %n, %x when used in printf style functions can lead to unexpected behavior, possibly crashing the application or even allowing unintended memory access. Encoding/decoding issues. If the application or network protocol uses character encoding, example UTF-8, URL encoding, certain byte values might be translated or dropped, corrupting your payload. Application-specific filters. Some applications deliberately filter out specific characters or byte sequences as a security measure. This is less common in basic buffer overflow targets but becomes more prevalent in real-world scenarios. In short, bad characters can ruin your exploit by preventing your shellcode from being fully written to memory, corrupting instructions, or triggering unexpected program behavior. 2. The bad character identification process, a step-by-step approach. The goal is to systematically identify which bytes within the range \x00 to \xff are considered bad by the target application. Here's the general methodology. 1. Generate a test payload. Create a string containing all possible byte values in sequential order, \x00, \x01, \x02, \x03, \xff. This is our alphabet to test. 2. Send the test payload *. Send this alphabet as part of the overflow, overwriting the return address, or other vulnerable buffer. 3. Examine memory, debugging using a debugger, GDB, OllyDbg, x64dbg, inspect the memory region where your payload was written. Specifically, look for where the sequence of bytes stops or becomes corrupted. 4. Identify bad characters *. Any byte that is missing, truncated, altered, or followed by unexpected values is a potential bad character. 5. Iterate *. Remove the identified bad characters from your test payload and repeat steps 2 to 4. This is crucial because the presence of one bad character might mask the presence of others. 6. Validation *. Once you think you've identified all bad characters, create a payload that excludes these characters and test it thoroughly. Make sure your shellcode executes correctly. 3. Code example, Python, and debugging demonstration, GDB. Let's create a Python script to generate the test payload and then use GDB to inspect memory. Explanation asterisk. Asterisk generate underscore badger underscore payload, asterisk this function creates the alphabet string. It iterates from 0 to 255, converting each number to a byte, dot to underscore bytes, 1, little. It excludes any bytes that are already in the bad chars list. Asterisk main, asterisk this function. Asterisk defines the overflow offset with padding. Adjust this value based on your specific target. Asterisk builds the full payload, padding plus alphabet. Asterisk prints and saves the generated payload into payload.txt, where it can be used for exploit testing. Asterisk bad chars list asterisk this list is initially empty. This is where you will add the bad characters as you discover them. Debugging with GDB, or olidbg/x64dbg. 1. Compile the vulnerable program asterisk make sure you have a program vulnerable to buffer overflow and has debug symbols. For demonstration, let's assume you have a program called overflow underscore target. Compile it with debugging information, example gccg overflow underscore target.co overflow underscore target. 2. Run the program under gdb asterisk gdb overflow underscore target. 3. Set a breakpoint asterisk set a breakpoint after the vulnerable function, example strcpy or gets, has been called. This allows you to inspect memory after the overflow has occurred. Asterisk break main, to break at the beginning of main to step through, finding your vulnerable function. Asterisk break asterisk 0x401172, address of the function after strcpy in this example. 4. Run the program with input asterisk run the program, providing the generated payload from payload.txt as input. This might involve using a pipe or redirection. For example, if your program reads from standard input. 5. Examine memory asterisk once the breakpoint is hit, use GDB's X command, examine memory, to inspect the stack, or the buffer you overflowed. You need to determine the address of the buffer. Let's assume you've determined that the overflowed buffer is located at address 0x7ffffffd000. Use x/256xb0x7ffffffd000 to display 256 bytes in hexadecimal format starting at that address. You can adjust the number of bytes displayed to cover the entire alphabet you sent. Asterisk the X command format, x/info address. Asterisk n, number of units to display. Asterisk f, format, x for hexadecimal, b for byte, s for string, etc. Asterisk u, unit size, b for byte, h for half word, 2 bytes, w for word, 4 bytes, g for giant word, 8 bytes. Asterisk address, the memory address to start examining. 6. Analyze the output asterisk look at the memory dump. The alphabet you sent should be visible, at least partially. Asterisk truncation asterisk if the sequence stops abruptly, example you see 000100203, then suddenly a bunch of 00s or garbage, \x00, or the byte immediately before the change, is likely a bad character. Asterisk alteration asterisk if certain bytes are replaced with other values, those bytes are likely bad characters. For instance, \x0a might be converted to \x0d \x0a, carriage return plus line feed, on Windows systems. Asterisk unexpected control flow asterisk if the program crashes or behaves oddly, it might be due to a format string vulnerability or some other interaction with the payload. 7. Add to bad chars asterisk in your Python script, add the identified bad characters to the bad chars list. For example, if you found that \x00, \x0a, and \x0d are bad. 8. Repeat asterisk rerun the script to generate a new payload excluding the identified bad characters. Repeat the debugging process, steps 2 to 6. Continue iterating until you are confident that you've found all the bad characters. Example GDB session snippet, illustrative. In this example ***, note, your output will be different depending on your target program. * we see the padding, A's, then our byte sequence 0x00, 0x01, 0x02. Notice that at 0x7 FFFFFFFD4D0 after 0xFF we have 0x00 then the padding starts again. Likely culprits are 0x00. Important notes address space layout randomization, ASLR, a security feature that randomizes memory addresses, can make debugging more challenging. You may need to disable ASLR, temporarily, during testing or use techniques to bypass it. In Linux, you can disable ASLR with echo 0 sudo t/proc/sys/kernel/randomize_va_space. Important re-enable ASLR, echo 2 sudo t/proc/sys/kernel/randomize_va_space, after your testing. Stack alignment some architectures and calling conventions require the stack to be aligned to a certain boundary, example 16 bytes. Misalignment can cause crashes. Pay attention to stack alignment if you encounter unexplained crashes. Little endian versus big endian make sure you understand the endianness of your target architecture. The code example uses little endian when converting integers to bytes. Target specific behavior the bad characters will vary depending on the target application and the environment. Don't assume that the same characters are bad across different systems. Format string vulnerabilities be careful when your payload reaches format string functions like printf. Inserting format specifiers can have unintended consequences. 4. Dealing with bad characters in shellcode. Once you've identified the bad characters, you have several options. Avoidance the simplest solution is to find or write shellcode that doesn't contain the bad characters. Tools like misvenom, from Metasploit, can generate shellcode that avoids specific byte sequences. Use the B option to specify bad characters. Encoding you can encode your shellcode to transform the bad characters into harmless ones. The shellcode then includes a small decoding routine at the beginning to revert the encoding at runtime. Common encoding schemes include XOR encoding, base64 encoding, and custom encoding algorithms. Misvenom also supports encoding. x86/Shikata_GA_NI is a polymorphic XOR encoder. Splitting and reassembling if avoidance or encoding is too difficult, you might split your shellcode into smaller pieces, write each piece to memory separately, and then jump to the beginning of the first piece to execute the entire shellcode. This is more complex but can be effective. 5. Advanced techniques and considerations. Dynamic bad character discovery in some cases, you might not have access to the application's source code or be able to easily debug it. You can use techniques like binary instrumentation or fuzzing to dynamically discover bad characters. Return-oriented programming, ROP If you can't inject shellcode due to bad characters or other restrictions, ROP is a powerful technique. ROP involves chaining together small snippets of existing code, gadgets, within the application to perform arbitrary actions. ROP bypasses the need to inject executable code. Real-world targets. Remember that real-world applications often have more sophisticated security measures, such as stack canaries, data execution prevention, DEP, and address space layout randomization, ASLR. Bypassing these defenses requires advanced techniques. In summary, finding bad characters is an essential part of exploit development. By systematically identifying and mitigating these characters, you can significantly increase the reliability and success rate of your exploits. This episode provided a detailed methodology, code examples, and debugging techniques to get you started on your path to mastering buffer overflows. Remember to always practice responsibly and ethically, using these skills for defensive purposes or authorized penetration testing. Good luck.